Welcome to AI Journal Club, the Digital Pathology Podcast segment where we take a closer look at the research shaping AI in pathology. This episode is one of our AI-powered summaries series, AI-generated deep dive into a paper worth your attention. It's curated from our weekly DigiPath Digest live stream that I run every Friday morning. I'm Dr. Alex Zhurav, and this is your shortcut to stay current. Let's dive into it.
Welcome back, Trailblazers, to another Journal Club-style discussion right here on the Digital Pathology Podcast. I am so glad you're tuning in today.
Yeah, thanks for joining us, everyone. We have a really fantastic paper lined up for you today.
We really do. We are digging into a brand new 2026 paper. It was just published in the journal Clinical Breast Cancer.
Right, and we should definitely credit the authors up front. It's by Yuliana Budi Susilo, Dewi Yuliana, Shamima Abdul Rahman, and Sulian Leong.
Exactly. And the mission for today's episode, for all of you trailblazers out there looking to optimize your own workflows, is to explore this really innovative in silico simulation study.
Yeah, which is basically a deep learning framework designed to automate the triage of breast cancer biopsies over in Malaysia.
And I think we need to establish right away why this matters for you, the listener. Because this isn't just about some cool AI theory, right?
Oh, absolutely not. No, this is about solving very real, very severe diagnostic bottlenecks. They're trying to fight a massive pathologist shortage and figure out how to make healthcare labs actually sustainable.
Right, because before we can even talk about the AI solution, we have to talk about the logistical nightmare they are trying to fix.
Yeah, the clinical reality is pretty grim. In Malaysia, breast cancer incidence and mortality rates they're just steadily rising.
Which means early diagnosis is quite literally the most critical factor for survival.
Exactly. But they are hitting this massive logistical wall. There is a critical shortage of qualified histopathologists.
Yeah, the paper mentioned the histopathologist to population ratio is falling below the World Health Organization's minimum recommendations. That is a scary metric.
It is. And the human cost of that shortage is measured in turnaround time.
Right, the TAT.
Yeah, the TAT. The study details that biopsy results are frequently taking longer than 2 weeks.
Oh, wow. So a patient finds a lump, goes through this, invasive biopsy procedure, and then just has to wait for over 14 days just to find out if it's cancer.
Yeah, 14 days of just pure anxiety. And a big reason for that wait time is the FIFO problem.
Ah, right. First in, first out.
Exactly. The system just operates on a strict arrival basis. Every slide that arrives at the lab just gets put at the back of the queue.
I was thinking about this when reading the paper. It's kind of like, imagine you're standing in a busy emergency room, right? You have all the classic signs of a heart attack. Your chest is tight. You're sweating.
Or in a highly urgent situation.
Exactly. But when you look at the line ahead of you, there are 80 people waiting to be seen for paper cuts. And the triage nurse just says, well, they got here first.
It sounds totally broken when you put it like that.
But that's exactly how this biopsy queue operates. Mm-hmm. And the crazy part from the paper is that 70 to 80% of these breast biopsies are actually benign.
Right. Meaning the pathologists are working at absolute maximum capacity. But they are spending the vast majority of their highly specialized time just confirming non-malignant tissue.
Which means the FIFA system is actively delaying the identification of the real aggressive malignancies. It treats a highly suspicious carcinoma with the exact same urgency as a routine fibroadenoma.
It's basically a functionally blind system.
So, okay, let's unpack this. If FIFO is failing so completely, how do we effectively sort the vital cases from the benign ones without just, adding a manual triage step that burns out the pathologists anyway?
Well, that is where deep learning comes in. It's structurally ideal for this kind of visual filtering.
Right, as a sort of first-pass screen.
Exactly. If an AI can scan the whole slide images, the WSI, it can flag the suspicious features and just automatically reorder the queue. Push the likely malignancies right to the top.
But there is a massive hurdle there, right? To train a deep learning model to find breast cancer, you need an enormous amount of data.
Oh, absolutely. And in a resource-constrained setting, trying to gather a massive, perfectly annotated local data set is, it's a nightmare for patient privacy.
Yeah, and data scarcity in general. Gathering thousands of sensitive medical records is just legally and logistically so complex.
So to get around that data dilemma, the authors engineered a really specific technical pipeline. They used a convolutional neural network based on a pre-trained ResNet 50 architecture.
Okay, hold on. Let's break that down for the listeners.
Sure, yeah.
They coupled that ResNet 50 with an attention-based multiple instance learning mechanism, right? The MIL.
Yes, exactly. Because, analyzing a whole slide image at 20x magnification is essentially like trying to process a high-resolution satellite map of an entire city all at once.
Right. The file sizes are just too massive. The computational load would fry most servers.
So the system actually divides the WSI into these smaller patches, 256 by 256 pixel patches to be exact.
Yeah. And the ResNet 50 network basically analyzes those individual patches, but the MIL, the multiple instance learning part, is what actually makes sense of the broader picture, right?
Exactly. Because in standard machine learning, every single image gets a label. But in a whole slide image, a tumor might only take up like a tiny fraction of the tissue.
Right. It's a needle in a haystack.
So MIL operates on the assumption that if even one patch in a slide shows malignancy, the entire slide has to be flagged as suspicious.
It's a highly localized search function, but I have to say the attention-based aspect of it is what I found particularly elegant.
Oh yeah, the attention scores are brilliant.
Right. It doesn't just average all the patches together, it assigns weights. It actively learns which specific cellular morphologies or, nuclear atypia are most relevant to cancer.
And it gives those specific patches higher attention scores while basically ignoring the vast expanses of healthy stroma.
It's so efficient. But okay, the most significant twist in this whole methodology is how they actually train that architecture.
Yeah, this is the really wild part. They bypassed the privacy and data scarcity barriers entirely by using a generative adversarial network.
Specifically, the StyleDanu2 ADA architecture.
Right. They used it to synthesize the training data. They generated 10,000 completely artificial whole slide images.
Wait, let me just pause you there. They generated 7,000 benign and 3,000 suspicious slides that are totally fake.
Yes. Completely artificial.
I mean, I have to push back on this. They trained a diagnostic medical AI on fake data. How can we possibly trust an algorithm to find real cancer if it learned from breast tissue that doesn't actually exist?
I know the skepticism is completely warranted. It sounds counterintuitive. But you really have to look at how these generative adversarial networks, or MISNNs, actually learn.
Okay, tell me.
Yeah.
Because it sounds like science fiction.
So a GAN is basically two competing neural networks.
Yeah.
You have a generator and a discriminator. The generator attempts to create realistic images from just random noise, and the discriminator tries to detect the fakes.
So they are constantly dueling with each other.
Exactly. They duel continuously. So the generator isn't just copying and pasting existing slides. It is actually learning the deep mathematical rules of tissue morphology.
Like how the cells cluster together, or how the chromatin is distributed.
Right, or how the stroma interacts with the epithelium.
Yeah.
And the ADA component, the adaptive discriminator augmentation, is super crucial here.
Why is that?
Because it prevents the discriminator from simply memorizing the small set of real seed images they used to start the process. It forces the generator to really understand the underlying biological patterns.
Rather than just mimicking the seed data. Okay, that makes sense. But how realistic are these fake images, really?
The validation metrics are actually highly compelling. They measured the visual fidelity using something called the Fréchet inception distance, or FID.
Right, which calculates the statistical difference between the real and the generated images.
Exactly. And their FID score was less than 25, which indicates exceptional realism.
But, statistical realism doesn't necessarily translate to clinical realism, right? A computer might think the math adds up, but a seasoned pathologist might look at it and immediately spot some structural impossibility.
Which is exactly why they did a blinded review step. It was so critical. They presented a mix of real and synthetic slides to 3 expert pathologists.
And what happened?
The human experts gave the synthetic images a plausibility rating greater than 90%.
Wow, over 90%. So they couldn't reliably distinguish the AI-generated tissue from actual patient biopsies?
Nope, they were that good.
That fundamentally changes the barrier to entry for digital pathology. Think about it. Hospital systems that lack these massive, centralized, annotated digital archives can still develop highly accurate diagnostic tools.
Yeah, they just need to leverage a small seed of local data to generate this huge synthetic training set.
Okay, so now they have this highly capable triage algorithm built and trained on synthetic data, but how do they safely prove it works?
Right, because dropping a newly minted AI directly into a struggling public health system to just see what happens is a massive operational risk. You can't just experiment on real patients.
Obviously not. So the bridge between the theoretical algorithm and actual clinical impact is the simulation, building a virtual hospital.
Exactly. They built an in silico discrete event simulation using a Python library called SIMPy.
A discrete event simulation, or DES. So how does that actually work in this context?
Basically, it models the operation of a system as a discrete sequence of events in time. Every event occurs at a particular instant and marks a change of state.
So for a pathology lab, that means tracking a slide from the exact moment it's accessioned to the scanner to the pathologist's queue right down to the final report.
Right, and they simulated this whole pathology department for 250 working days, processing 5,000 hypothetical cases.
Which is like a highly sophisticated digital twin, or honestly, kind of like a healthcare video game where researchers can just safely stress test different triage policies.
Yeah, that's a great way to put it, but the value of a simulation is entirely dependent on the parameters you code into it. A frictionless virtual environment doesn't prove anything.
Right, you can't just pretend the lab has infinite resources. And the authors were incredibly specific with their real-world parameters.
Oh yeah, they constrained the virtual lab to mirror reality perfectly. Exactly 2 pathologists, 3 technicians, and 1 slide scanner.
And they set the case arrival rate at 20 cases per day.
They also modeled the human element, which I thought was really smart. They used log normal distributions for reading times.
Because a pathologist doesn't spend exactly 10 minutes on every single case.
Exactly. A straightforward fibroadenoma might take a few minutes, while a complex borderline malignancy could take hours.
So by using empirical hospital data, they calibrated the simulation to reproduce the hospital's actual historical turnaround times.
And they got it to within a 5% error margin of baseline reality.
That is impressively tight. Okay, the board is set. So what happens when they press play and pit the AI triage system against the old FIFA system?
Well, the baseline performance of the algorithm inside the simulation was really robust. The AI achieved an area under the curve, or AUC-ROC, of 0.984.
Which is fantastic, but in a triage context where the whole goal is to filter cases without missing a single malignancy, sensitivity is really the paramount metric.
Right. A high AUC is impressive, but avoiding false negatives is the real test. And the model demonstrated a 96.5% sensitivity and a 94.2% specificity.
Okay, and 96.5% sensitivity means this AI is a highly secure first-pass filter. It's catching almost every malignant case and bumping it up the queue.
And the 94.2% specificity ensures it isn't just clogging that priority queue with false alarms.
But the translation of those metrics into actual patient wait times is where the simulation really proves its value.
Definitely. So under the traditional FIFO system, the turnaround time for suspicious malignant cases averaged 7.24 days.
Okay.
When they activated the AI triage protocol, that wait time plummeted to 4.47 days.
Wow. That's a 38.3% reduction in turnaround time for the most critical patients. That is nearly 3 days of recovered time before a patient can consult an oncologist.
It's massive. And they actually tested alternative policies, too. They tried a purely clinical rule-based system, prioritizing cases based on patient age or family history.
And how did that do?
It only reduced the wait time by 12.1%. And a hybrid system using both clinical rules and AI only achieved a 29.4% reduction.
So the pure AI analysis of the tissue itself absolutely crushed the other strategy.
It really did. But managing a queue always requires a trade-off.
Right. Here's where it gets really interesting. Because when you pull the 20% of malignant cases to the front, the remaining 80% of benign cases get displaced backward.
Yeah, the data definitely reflects that displacement. Under the FIFO model, benign cases waited 6.53 days. But under the AI triage model, their wait time actually went up slightly to 7.15 days.
So the wait time for benign cases increased. But clinically, an additional half-day wait for a non-urgent benign diagnosis is a highly acceptable strategic compromise, right?
Absolutely. The core tenet of medical triage is resource allocation based on severity. Delaying a benign cyst diagnosis by 12 hours to accelerate a carcinoma diagnosis by 3 days. That is the definition of system optimization.
Yeah, and across the entire 5,000 case simulation, the aggregate turnaround time still decreased by 13.2%.
Plus, we have to talk about the secondary impacts.
Yeah.
Patient outcomes are primary, but the effects on staff well-being and lab resources are huge. Pathologist burnout is basically the root cause of the backlog anyway.
So how did the AI affect the workload?
By using the algorithm to intelligently route and batch the benign cases, the overall pathologist workload dropped by 22.5%.
22.5%. The paper calculated that efficiency gains saved 422.2 hours annually.
Which is the equivalent of adding 0.68 full-time pathologists to the department.
They effectively generated a 2/3 of a highly specialized medical professional simply through algorithmic queue management. That is wild.
And those recovered hours can be redirected toward, complex multidisciplinary tumor boards, teaching, or just managing difficult, atypical cases.
But the optimization wasn't just human capital. It extended to the physical laboratory resources, too.
Yeah, the AI-driven workflow reduced overall reagent and slide consumption by 15.2%.
Now, for the trailblazers listening, you might wonder why we care so much about reagent use. But this touches on a massive shift in clinical operations.
Right, the whole green laboratory initiative.
Exactly. Global healthcare sustainability is becoming so important. Reagents used in histopathology are frequently toxic, they're costly to procure, and they require highly regulated, expensive disposal protocols.
So lowering material consumption by 15% is a dual incentive for healthcare administrators. It proves AI can be both clinically and environmentally beneficial.
It's a cost containment strategy and an environmental measure all in one. Faster, greener, and demands less expert labor. It sounds like a silver bullet.
Well, we do have to ground the excitement a bit.
Right, the reality check. So what does this all actually mean? Can hospitals just download this simulation and fix their backlogs tomorrow?
Definitely not. We have to remember the limitations of the study. This is an in silico simulation based on synthetic data. It is not a clinical trial.
Because a simulated environment assumes flawless integration, right? It assumes the laboratory information system has zero network latency when transferring those massive image files to the AI server.
Exactly. And it assumes the slide scanners literally never experience mechanical downtime, which anyone who works in a lab knows is, well, it's a fantasy.
Yeah. And there's also the reality of physical slide variations. Real-world slides suffer from tissue folds during sectioning, or variable stain uptake depending on the batch of hematoxylin in use.
Or even digital artifacts introduced by different brands of scanners. The AI was trained on a highly realistic, but ultimately controlled, synthetic data set.
So the algorithm's 96.5% sensitivity could fluctuate wildly when exposed to the daily physical inconsistencies of a live, messy laboratory.
Right. Plus, local population genetics and specific environmental factors influence histological presentations. So a model trained on one subset must be rigorously validated before you apply it to another.
Which is why the authors state the essential next step is a prospective clinical validation trial on a real physical data set from a Malaysian hospital.
Along with a comprehensive economic analysis. Because yes, a 15% reduction in reagents is economically favorable. But the upfront capital expenditure to digitize a pathology department purchasing high-throughput scanners, server farms, IT infrastructure, it's an immense initial barrier.
For resource-constrained systems, it's a massive hurdle. But wrapping up here, the value of this paper for all of you trailblazers listening is that it offers a simulation-informed blueprint.
Yeah, it mathematically demonstrates that the potential return on investment is structurally transformative. It shows how you can speed up critical cancer diagnoses by 38% and save massive amounts of expert time.
Before we go, though, this whole deep dive left me with a really profound, kind of unsettling thought.
Oh, yeah. What's that?
Well, if synthetic data generated by adversarial networks is already realistic enough to train highly sensitive cancer-detecting AI, are we approaching a future where the most powerful medical tools we have are built entirely from the digital ghosts of patients who never even existed?
Oh, wow. Yeah, that is...
Right. And if so, how will that totally change our definition of what clinical evidence actually is? How do you audit an AI when its foundational truth was hallucinated by a machine?
That tension between synthetic innovation and real-world accountability, that is exactly where the next era of digital medicine is going to be defined. It's a huge epistemological shift.
It really is. Well, trailblazers, I encourage you to think critically about that and about how workflow simulations could impact your own clinical environments. Thanks for exploring the deep details with us. We'll catch you next time on the Digital Pathology Podcast.
That's it for this AI Journal Club episode. If you want more like this, make sure you're subscribed to the Digital Pathology Podcast. And come join us for the DigiPath Digest, our weekly live session. During these live streams, you can vote which paper becomes an AI deep dive. And if you're serious about digital pathology, grab my free book at digitalpathologyplace.com. This is the best place to start your digital pathology journey. Thank you so much for listening, and I'll talk to you in the next episode.